get started. A couple minutes early, but we can start. So we are going to switch from virtualization to a new topic. Okay, last time we finished virtualization. We are going to move on. Today we'll talk about code and process migration. Okay, and then if time permits, I will then start discussing communication in distributed systems, okay, which will be chapter 3 or 4 or something like that. Okay, so let me start with what is the motivation for code process migration. We'll talk about how it occurs. We'll talk a little bit about migrating resources, give you some details about process migration and how this might work using virtual machines. Okay, so that's the agenda for the class. Okay. I mentioned process migration maybe 2 or 3 lectures ago when I was talking about distributed scheduling. Okay. Remember when I said if a machine needs to offload some work to another machine, there are 2 ways to do this. One is you take a newly arriving request and just start that process in a new machine. Okay? Or you can take an existing process and move it. Okay? So the latter is going to be called process migration, and the first one is going to be called code migration. Okay? So it provides us with better performance, more balanced system. It gives us flexibility, ability to move applications around, and so on. Okay, and so in the context of migration, we will talk about 2 approaches. Okay, process migration, which is called strong mobility. Okay, this involves moving an actual process and executing process from one machine to another. We'll see it's a complicated task. It needs to deal with a lot of issues of how that is going to work. Okay. And the advantages are clearly it gives you a more balanced system and hence better performance. I mentioned Condor as a very brief case study 2 or 3 classes ago. Okay, Condor has in it the notion of process migration. Okay, I also talked about Sprite. If you remember, Sprite was a research operating system that was developed at Berkeley that implemented distributed scheduling on a cluster of workstation. Sprite was one of the early systems that implemented within it process migration. Okay. The other approach is called code migration. This is also called weak mobility. Okay. In code migration, you are actually shipping code and then executing the code as a process. Okay, you're not moving a process, rather you're just moving a program or some piece of code and you execute it on a different way. Now this arises in many common scenarios today. Okay, not just a distributed system. Okay, so web forms, if you fill a web form on a browser, okay, and hit submit, that is an example of code migration because some data and some code is sent off to the server for processing. Okay. If you write a query, okay, and then send it off to a database, that's an example of code migration where the SQL query that you wrote is a small program. Okay. You send that code off to a database server, the database server executes it. Okay, maybe in this case it's a remote database server. Okay, search engines where you type keywords are essentially queries. They're tiny programs that they search for all documents that have these keywords in them. Okay, and that code is actually executed at the server. So even in common scenarios like filling out a web form or executing a search query, we have code migration. Of course, we look at it more generally from a distributed systems perspective, not just these simple examples, web search or form filling. Okay? So 2 techniques, process migration and code migration. Okay, in one case, the code moves and executes as a process. In another case, the process itself moves. Okay? Now, there are many scenarios where moving this code is actually can be used for achieving many different tasks. Here is an example of using code migration to install drivers on demand. Okay, so if you all know what a OS driver is. Whenever you attach a new hardware or you buy a new printer, you have to install a driver so that the OS can then communicate with the device and enable it to function properly. Okay. Typically, what happens is the device might come with a CD or a USB drive which has the driver in it. You connect it to your machine and you install it. Okay? That's how drivers have been installed on machines for decades. Okay? Now that model is slowly changing, okay, and rather than shipping drivers with devices, a new model that has arisen is there is a repository of drivers, okay, that maybe the OS vendor is maintaining. Okay, so Apple might have a driver repository, or Windows might have a driver repository, and so on. Okay? And when you connect a device, okay, to the client machine, okay, the client machine is going to say, let us look for a driver in the repository, rather than asking the user to say, I don't know what this device is, go install a driver. The OS might say, do you want me to look for a driver? Okay, and if you say yes, it will go to the driver repository, and if it finds a matching driver, it is just going to download it and install it and configure it for you. Okay, this makes it much more convenient to add hardware or connect new hardware to your machines, whereby you don't have to figure out now where do I get a driver for this thing. Your OS will do this for you. Okay, this is now implemented even in things like the Mac OS X, at least for printers. If you connect a new printer, OS X will say, do you want me to look for a driver? And it will go to a repository and fetch a driver for you. If it cannot find it, of course, you are back to the old model where you have to manually install it. But that's an example of code migration. The reason I mentioned it is a driver is a piece of code. It's resident on some server. The client is downloading it on demand, installing it and using it. Okay? It's not what you might think of in the context of distributed scheduling or load balancing, but it's nevertheless an example of code migration. Okay, is that clear? Any questions on that? Okay, so that gives you an example of the flexibility, not just the performance side of it. Okay, now let us look at this in a little more detail. Okay, so we are going to go back to our process example and talk a little bit about process migration and code migration and so on. Okay, so let's assume that the program starts as a file, a binary file on disk. It could be a script as well, doesn't matter. It's a piece, some file on disk. Either you wrote a Python script or you wrote some C code and you compiled it and it's a binary. Okay, that's a program. Okay, now when the program executes, it becomes a process. Okay, this is what I mentioned earlier. Typically, this process is resident in RAM. Okay, that's your process. The process has multiple segments associated with it. If you remember, I mentioned that every process should have at least 3 segments, in many cases more. And the segments include the code segment, which is essentially this code that's being, machine code that's loaded in memory. Okay, what are the other segments? Stack and heap. Okay, there are many more, okay, but these are the 3 common ones. Stack and heap are data. Okay, the code segment actually has code, so you basically have at least these 3 segments associated with it. Okay, now when you think of this from process and code migration, you need to have this picture in mind. Okay, so if you have weak mobility or code migration, what's essentially happened is the user has told the OS execute this program. Okay, and what the system will do is, will basically, if there's a remote machine, okay, you will actually transfer this code and then construct a process. Okay, basically, you move the code and start a new process on that machine. Okay, that is code migration. Okay, so in this case, you're just moving this program over and you're executing it locally as if that command were given locally on that other machine. Okay? And if on the other hand, you are doing process migration, okay, there's already an existing process, which is resident on machine A, that's machine B. You have to migrate this entire process over. Okay? That means essentially moving the memory state of the process. Okay? Essentially all of this information, okay, the code, the stack, the heap has to be copied over to the other machine. Okay? If there's any kernel data structures, you have to recreate them on the other machine. At that point, the state of that process has moved over. You can resume execution. Okay. Now, needless to say, this is a complicated process. Machine A and machine B have to be homogeneous. Okay. You can't take a Windows process and just move it to some other operating system. It's not even going to make sense. Okay. Each OS has its own format for processes. It has its own kernel data structures. So process migration involves homogeneous machines. and it will involve, in most cases, it's going to involve pausing the process. So you can't just have the process execute while you're copying it over, because the memory contents may change while it's executing. Okay? So if you want to migrate a process, you are going to pause the process, which means you won't actually schedule it. So its memory content stays static, don't change. Then you take all of this data, okay, and it could be a lot of data if it's a large memory process, takes a lot of memory. You copy it onto machine B, any kernel state has to move over, etc. And then you have now this captured the state of the process as it existed on machine A on machine B, okay? And then you can resume execution of that process there, okay? And there are many more details. That's just the basic thing that you have to do. There are many more details associated with process migration, as we will see, but that's just moving the memory state of the process over. Okay, so that is called process migration. Okay, and so talked about, so you essentially have to move the code resource, which is essentially, I shouldn't say execution code, and data segments, okay, which is stack and the heap and so on. Okay. Now, there are other dimensions we'll talk about, and I'm going to come back to this picture and talk about other nuances that we just glossed over in order to make it practical. Okay? And those nuances are, those issues are, who's initiating this migration? Why did the migration happen? It could be sender initiated or receiver initiated, which in sender initiated, the machine that is where either the command was given or the process is running is the one that is offloading the code or the process. Okay? And when we talked about distributed scheduling, we said sender initiated versus receiver initiated scheduling. So you might have scenarios where the sender is initiating the migration. Okay, this is also true if you are a user who is submitting a SQL query to a database. You are the sender, you're sending your SQL query, you type it up into a database console and say execute. That query is going to be sent off to the database server. That's also sender initiated. The user is the sender, or the user's machine is the sender rather, and it's sent off the code to the receiver, okay, which is where it's going to execute. Okay, receiver initiated is the other way around, where the receiving machine is the one that initiates saying send me the code or the process, and it will execute it. Okay, that we saw that in the context of distributed scheduling. Another example of receiver initiated could be a Java applet or a Flash program. Okay? Your browser is the receiver. The browser says load this applet from the server. The code for either the Flash program or the Java applet resides on the server, on the web server. Okay, your browser is connecting to the web server, either downloading the Flash code or the Java applet and then executing it locally. Okay? So in this case, it's the receiver that is telling the server to send it the code. Okay, this is code migration, clearly not a process migration, and you're executing either the Java applet or Flash or whatever it is. Okay, so you can have the sender initiate the migration or the receiver initiate the migration. Okay, and then the last point is after the code or the process moves, what is actually happening to it? Okay, who's executing it? How is it executing it? So on. Okay, when you move code, you have the option of starting a new process. That's the default. In this case, you have a program. You want to execute this program. You move the code to this machine and start a new process. Okay, so in this case, the code that has migrated is executing a new process. Okay, or you can actually execute the code in the process that initiated the migration. This is true if you have a browser. Okay, browser downloads the Java applet. The Java applet is executing in the browser process. You don't start a new process. You could, but in this case, you're simply executing it in the process that initiates the migration. Okay, so the code can run in the process that triggered the migration, or the code can move over and a new process could be started. Okay, so those are two variants of how code migration works. And in process migration, you have two techniques to implement this process migration. One is just migrate the process, which is what I just mentioned here. You pause the process, you take the memory contents of this process, you copy it over, so on all of the other registers and everything have to be copied over kernel data structures. Then there's a snapshot of whatever the process looks like on machine A or machine B. You just resume execution as if it actually originated there. Okay, that's called migrating the process. The other technique is called remote cloning, which essentially does the same thing, but you are cloning the process. Okay, so you make a clone of the process, and in this case, even the parent process can continue, or if the parent process is terminated, it just looks like process migration. You paused it, moved it, and so on. But if you just clone it, you can have a parent and a child process, a clone. Both of them look exactly the same and both can continue. In that case also the process has migrated, but the parent process is still there. Okay, it's just doing something else afterwards. Okay. So that's also a technique that is available for implementing process migration. Okay, yes,
Is
question.
remote cloning used for executing a different thread? Is that primarily why it's used to execute a thread of a program while one other thread continues?
Okay, so why is remote cloning used, or what is cloning used for? Cloning is typically used to quickly replicate the application. If you just need a replica, or you need to have two processes that will then take over the load that is coming in and so on. So it's basically used more for replication. Migration is simply, there's only one process, you just move it over. So that's used for load balancing, saying this machine is overloaded, move the process and run it somewhere else. So the load has moved over. In cloning, you're just saying, I just need more server processes, so let me just clone. If you remember, fork also creates a clone. Okay, the fork system call actually creates a clone of the parent. That's just local cloning. Okay, so local cloning is just fork, which every OS supports. Remote cloning is just, think of this as you do a fork, but the child process appears on a different machine. Okay, that's one way to think about it. Yes.
In the case when a process is using dynamic link library, does that cause complications at all?
Okay, good question. Question is, if the process is using dynamic link library, is that going to cause complication? There will be lots of complications. One of them is to think about how libraries work, and that's coming up in 2 slides. We'll talk about that and lots of other issues. This just looks conceptually straightforward, but it is not. We just sort of made it a little simplistic just for us to convince ourselves it should be possible. But there are lots of problems. Okay, so let me first show you all the permutations and combinations we talked about, then I'll address this question that was just asked, saying what happens to libraries or lots of other things that might go wrong. Okay, so essentially migration could be strong or weak. Strong migration or strong mobility is just process migration. Weak mobility is code migration. Within each, you can have either the sender initiated it or the receiver initiated it. Okay? And then for each of those, you have this thing that says, where should I execute the process? Is it going to be a separate process? Is it going to be in a target process? Or are you going to clone it or migrate it? Okay? So all of those combinations. So in the end, if you take each of those dimensions and you can then make a different combination, you'll have various different variants of process and code migration. Depends on a sender versus receiver, target process, new process. So you'll get all of these combinations. Okay? So that's really looking at it at an abstract level. We'll go into now more details of what are some things that could go wrong. Okay? Any questions on this before I move on? Okay? Okay, so the main issue that you have to deal with, okay, is not how to move copy memory, but what happens to resources that the process was actually going to access over the course of its execution. Okay? It's easy to move a process, okay? But if there are resources the process is actually accessing, and if you cannot deal with those resources well, the process is not going to function. And there are many kinds of resources. Okay? The simplest example you can think of is there is a process running. Okay? Let's say it's process A. Okay? Is reading or writing to some file that's on the local disk. Okay? Now you just move that process over. Okay? If it tries to read or write to a file on that new local disk, then that's going to have some problems because you already have something you've written here. Okay? Either it has to continue to write to that original file from a remote machine, or you have to move that file over as well so that it can continue as is. Okay? A file is a resource, it's a disk resource in this case. Okay? And then there was another point that was actually raised, which is libraries. Okay? So when you run a process, typically you link many libraries that are on that machine. Okay? If you execute a C code, you might link to the C library or the math library or whatever. If you're running a Java program, you need a JVM. Okay, it goes without saying that if you don't have a JVM, you cannot run the Java program. Okay, now, if you are moving a process over, okay, you need to make sure that somehow those resources that were actually associated with the process exist in some way on the new machine, or they move with the process. Okay? It's not just moving the process. Either you have to move the resources, or you have to find new resources that will take the role of whatever the original resources there. So in the case of JVM, you just need to make sure that the same JVM version is available. You can't just arbitrarily run it on something else. It might behave differently. Or if there are libraries, you want to make sure the same versions of libraries are present and so on. Okay? And then there may be hardware resources, okay, like a printer. Okay, so if you had a printer that was connected here and the process was in the middle of sending a print job, say, okay, if you just move it over and clearly you're not going to migrate a printer. That doesn't make sense, right? So you have to figure out how you deal with hardware resources. Okay, are you going to find a new printer? Are you going to send the job over a network to the old printer? What is it that you are going to do? Okay, so these are all examples of resources that are being accessed by a process. Okay, and when a process moves over, you have to answer the question: what's going to happen to the resources it were using? Okay, how are all of those handled? Okay, and the most complicated case is network resources. Okay, if you had process that was actually communicating, it had open socket connection, it was communicating to another process, you simply move this process over, okay, and you don't do anything specific, your TCP connections are going to break. Okay, and the reason is this machine is going to have a different IP address than this machine. If the other end is going to just send packets to, because packets are sent to an address, not to a process. It's sent to IP address and a port number, okay, not to a specific process. So the packets will continue to arrive to this IP address and a port number on this machine. The process has simply moved over. Okay, the other machine, the other end doesn't even know that has happened. Okay, so if you have network communication, those are often the thorniest problems that you have to deal with. In fact, it's much harder, and many process migration techniques will not even move a process if it has open socket connection, unless there is something specific you do about it. Okay? So these are all things that are going to complicate, okay, so our process migration, okay? And even in some cases code migration. So this simple notion that I can just pause the process, copy its memory, and just resume execution is not that simple. Okay, you have to deal with all of these challenges. Okay, is that clear? All right. So now question is, how will we do it? Okay, what techniques could we actually use, okay, that will allow us to deal with all of these problems? Okay, and to do that analysis, we have to understand in a little more detail what kinds of resources the process is actually using, and we are going to classify resources into multiple categories. Okay, and so the three categories are, we will classify them by identifier, by value, or by type. Identifier specifically says that there is a unique resource that the process is accessing, and you cannot replace it with anything else. So a website or a URL is an example of a unique resource. Okay? If you have a browser that is actually going to go to a web server and download a web page, you can't just substitute it with some other URL. Doesn't make any sense at all. Okay? So URL is an example of a unique resource, and FTP server. These are all resources that have a specific identifier. They are not replaceable or substitutable by something. You can't substitute it. So you have to continue. If you are going to move the process, somehow you have to make those resources accessible from the new machine. That's the only way your code is going to work. Okay? Now, if you might have resources that are classified by value, okay, or in this case, it is C library version 6.3, okay, or JVM that support Java 1.7. Okay, so now, so if your receiving machine has the same version of the library or the same version of the JVM, that is acceptable to us. Okay, that's a good enough substitute. We can make it work. Okay, other versions may not work, but so long as you have the same version, we are good. Okay, so in this case, you can substitute one resources for another so long as they are exactly the same, okay, on a different machine. Okay, and the third one is resources by type. Okay, and this is the weakest binding. Okay, in some sense. So what that means is the process, like printer is an example of this kind of resource. The process wants to print to a printer. Okay, it doesn't care. Maybe it wants to print to a color printer. It doesn't care if it's a HP printer or a Canon printer. You just want to print. Okay, so there is even more leeway in what is substituted. You don't even need exactly the same model or something. So long as you can print, and you are happy. Right, the process is happy that it fulfilled whatever it was trying to do. So this is a different kind of resource. Here, what you can substitute with, it becomes even more flexible. Okay. So in the first case, there is no way to substitute. You are actually trying to access something very specific, and that's the only thing you can allow the process to access. Here, you can do some substitution so long as it's of the same type and so on. Here, or rather of the same version. Here, you can basically just say same class. It doesn't really matter. Okay. So that's one way to think about resources. Okay. Another way to think about resources is how attached it is to the origin machine. Okay. And so again, we'll have three different things here. So one says it's unattached, which means you can freely move it around. Okay. A file is an example. If this process or reading or writing to a file, you can copy the file over or move the file over. Okay. So that's not particularly attached to a machine at all. Okay. Okay. Fastened resources are resources that can be moved, but at a high cost. Okay. That means they have some stickiness to this machine. Okay, you could move them if you want to with the process, okay, but the cost is going to be high. Example is a large database. Okay, let's say the process here was accessing a local database. Database is 10 gigabytes in size, and not a small database. Okay. So if the process moves, you could certainly move the database, but you have to pay the cost of moving a lot of data over a network. Okay. So long as you're willing to pay the cost, that's okay. Otherwise, it will probably require you to somehow provide access to the database without moving it. Okay. So those are called fastened resources. Unattached resources says move it freely, it can be moved cheaply, so there's no problem. You can move the resource with the process. Okay. This one says you can move it, but the cost is high. Okay. The last one says they are fixed resources, they cannot be moved. Okay. Hardware resources. If the printer is connected to this machine, okay, you can't move the printer. Well, a human has to move the printer. It's not going to move by itself. Okay. Or you have network socket connections. Okay. Those are attached to the machine because they're specific to an IP address and a port number. That's not something you can move over because this machine will have a different IP address. It doesn't even make sense to think about moving it over in that sense. Okay. So fixed resources are resources that cannot be moved. So you are going from something that's very flexible, resources can be easily moved, to they're expensive to move, to they cannot be moved at all. Yes.
What do you mean by website and fastened resources?
Okay. What do you mean by website and fastened resources? This just says web content, not the website as in a URL. It might be a lot of data. So if this was a web server and the web files were here, there's a lot of content, you're going to move that over. Okay? So it's a website, not a web server. You had a question there.
Yeah, that's almost the same thing.
Okay, all right, yeah. Okay, so just think of them as resources that involve a lot of data copy. That's all you really need to worry about. Okay, so those are the kinds of resources. Now let's ask the question: what options do we have if a process that's accessing any of those resources moves from machine A to machine B? Okay, and I'm going to show you some options. Okay, so here are options that are available to us. Okay, so there are 4 options. First one says global rebinding. Okay, not rebinding, global reference. Yes, then you have move, you have copy, and you have rebind. Okay? And what this essentially mean is, this essentially says provide remote access. Okay? Global reference essentially the process is moved. Okay, just make it access the original resource remotely. Okay? The resource is not moving essentially. You just provide access to the resource over a network. Okay? That is called global reference, meaning I can actually continue to access that resource from a different machine over a network. Okay, move essentially says I move the resource. Yeah, I actually take a file and move it over. Copy just says I make a copy of the resource. So there will be 2 copies on machine A and machine B. Move essentially is like moving a file. Okay, copy is just copying a file. So when you do copy, you have 2 copies of it. Okay, and then the last one is saying rebind. This way nothing is moving. Just find a local substitute for the original resource. Okay. So those are the 4 options that are available to us. Okay. And now here is a table that on the column says, is it an unattached resource that we are trying to figure out what to do, or a fastened resource or a fixed resource? Those are the columns. And the rows are how tight is the binding? Is it by identifier? Is it by value? Is it by type? Okay. So the 3 things that I talked about as far as the binding is concerned, and the 3 things I talked about as far as the cost is concerned. Okay. So we have 9 different combinations of, is it an unattached resource that's identifier, is a fastened resource, all of these combinations exist. Okay? And these are the choices that are available to us. Okay? And by and large, okay, there are lots of options in the table, but by and large, the way to think about this is as follows. If it's an unattached resource, which means it's easy to move, okay, you can always have the move option available to you. Okay, so it's easy to move. It doesn't matter as identifier, value, type, but if it's easy to move, move it over. Okay, so that's basically, you'll see that move always exists here, okay, as an option. There are other options because other things also are feasible. Okay, this is just showing what are all the things that are feasible, but by and large, the preferred option is if it's unattached, move it. Okay, and this column says it's a fixed resource; it cannot be moved at all. And then the main option for you is to say provide remote access. So you will see that GR essentially is an option in this column. Okay, there are other things also, but the main option is saying provide remote access. Here is it's cheap to move it. It doesn't matter. Okay, and then if you now look at the rows, okay, if you say if it's by type, which means it's loose binding. Okay, so the type just says printer. Okay, so you will essentially say rebind is always an option in this row, as you will see RB appears everywhere. So if it's by type, why even bother doing anything? Just find another local resource and substitute it. If there's another printer attached to machine B, use it. Okay, doesn't matter that it's not the same HP printer. If it's different model, who cares? Okay, so you'll see that rebind is always going to be there here. And if you have by identifier, that means that that's the unique resource you want. You'll see that remote access is also option in that column. Okay, so or in that row rather. Okay, the only problem is what you do in the middle, where it's expensive to move, and you'll see there are lots of options. In some cases, you will say I'm going to move it. It's going to be high cost, but let me move it anyway. In other cases, you might say if it's expensive to move, why bother? Let's just keep the resource there. So I'm going to do a rebind, or not rebind, rather. I'm going to allow a global reference and provide remote access. Okay? So here you have some choices that you actually have to think carefully. What matters really? Okay, how much is the cost? How much data copying is involved? Should I actually copy it or not? That's just a question.
Please, can you throw more lights on the rebind?
What is the question?
On the rebind. I'm not really
What is rebind? Is there a question? Okay. So rebind essentially says that rebind a process to a locally available resource. What that essentially means is if there is another resource that is of the same type on the new machine, just use that instead of the original resource. Okay? And the example I gave was there is process A is trying to print to a printer. Okay? The printer is your resource. Okay? If this process moves here, okay, you basically just find another, if there's another printer here, okay, you just say that rather than printing there, print to a local printer. Okay? And the important point is we don't actually care that these are exactly the same types. Maybe this is an HP printer, that's a Canon printer. It's a printer. That's good enough. Okay, you don't even have to have an exact match. So it is a loose binding. So you can just say find another substitute for the original resource and use it instead. That's what rebinding means. So you are bound to this one. Now you are rebinding to a local resource of a similar type. Okay, is that clear? What that table is? So again, there are many other options, but the real takeaway is if it's unattached, you would rather just move it because it's cheap to move. If it's fastened, you just rather provide remote access. If it is a loose binding by type, okay, then you can just look this way, saying you can also do rebind. Okay, because you can just say why, even if it's unattached and it's by type, why even pay the cost of moving it when you can just substitute it? So you would actually then over copy or something you're going to do rebind. So rebind is always an option. And if it's a byte identifier, then you have to actually provide remote access as one of the options. Okay, so that's the way to really think about all of this. Any questions on this? Okay, this is an abstract discussion, but it captures all possible scenarios that you might actually have to think about in a real process migration system. Okay. So I'm going to now go back to our network sockets problem and think about, now with this in mind, let's say you have a process that was communicating over a network. Okay, you move it over. Okay, what design decisions will you make? How will you actually make sure that it can continue to communicate uninterrupted? Is that clear what the problem is? And I'm not asking you to tell me what are you going to change on TCP or anything like that. I'm just simply asking, given these options, what could you do?
Global reference.
Okay, so you're going to do global reference. That is true. Okay, because you cannot change the IP address of that machine is going to be different from this machine. If this process is communicating, there's a socket that has an IP address and a port number. The socket is actually has the address of the machine, not the address of the process. So if you move the process, you cannot actually change the address of the machine. That's not going to happen. Okay? So you have to do global reference, okay, which is what we said is the only thing you can do. Okay? But what does that mean? Okay, so now I moved the process, right? The process is here. Okay, there is still a socket here that's hanging here without a process. Okay, that is actually connected to some other machine. Yes.
At the application level, can you have the process have some sort of it maintains the connection even if it needs to reestablish the connection through the sockets at the TCP level?
Okay, question is, can you do something at the application level so it can maintain the connection? Right, that's your point. So you have to do something like that. So what does global reference mean? It means provide remote access. Okay. So now somehow this process needs remote access to that socket which it left behind. Socket didn't move. Socket cannot move. Socket is tied to the machine. Okay. So you have to provide remote access to this socket. So what you are actually going to do is when the process moves over, there's going to be a new socket here which will have the IP address and some port number on this machine. Okay? So you just use this remote access as a forwarding mechanism. Like I forward my mail. Okay, if you move to a different apartment, you forward your mail. Same thing is going to happen here. The process moved, it now has a new socket here. You just tell the machine here saying whenever a packet arrives for this address and that port number, simply forward it to that address and that port number. Okay? And when this machine makes a reply, it's going to actually send it back here and this is going to forward it to the original client that sent the packet. Okay? So in this way, this can be made transparent. Okay? The connection can stay alive. Okay? It is complicated to implement. Okay? This is again seems easier than it seems. Okay, but the basic concept is you're going to use forwarding. Okay, you basically cannot change the IP address here. Okay, so you will have to keep that socket there. You have to essentially say remote access, which is global reference. What that essentially means is this will stay alive even though there's no process here anymore, and the OS has to do something extra. Okay, yes.
That's what I was going to ask. Does that require operating system support or just the application?
Yeah, it requires OS support. It's not that trivial. Okay, and there is actually there's a notion of mobile IP where this actually is implemented. Mobile IP, if a machine moves and it changes its IP address, you have a home address which is going to forward the packet. You can use techniques like that, but it requires some changes. It requires explicit protocol support and things like that. If you set up a route here, okay, so routing, you could do routing, but the routing is essentially for address space. Here you are essentially, you have to do something in the IP table saying whenever a packet arrives for this IP address and this port number, forward it there, and here you have to say whenever I receive a packet from here, it's actually meant for this process. So it will be implemented by setting up IP tables and so on. But the basic concept is you have to still be able to do this kind of stuff very carefully. Okay? Yes?
So we haven't really freed up all the resources on machine A at this point, so it seems kind of wasteful.
Okay.
Like, couldn't we reestablish a new connection?
Yes, so I think that's a good point. Point is you left some resources back, so it seems rather wasteful. So you did free up some resources, which are memory resources, CPU resources got freed, you moved them over. network resources couldn't be moved, unfortunately, so we left them back. So it did not offload everything that was associated with the process. But that's the only choice. You have to make this work this way. Okay? You asked a different question saying, could you not let the connection break and re-establish? Of course, you could do that as well. That is not transparent. Okay? This requires both endpoints to know that connections might break and you re-establish the connections. Okay? So that's also an option. And there are some applications, most applications that try to do anything like this is actually going to do what you just said. Connections break and they are going to re-establish the connection. Okay? So you retry saying TCP connection broke, and then, but that it's not transparent. The other end better know that that is what is happening. Okay? If you just see a connection break, some weird thing might be going on and you might just not. So it requires applications to be aware, and it's not going to be as transparent anymore. So you can make different design decisions based on how transparent is it. Does the application code have to change, or does it work as is? Okay, so depending on that, you can make different decisions.
That's what I was going to ask. This is independent of what's running in the process, right? So
Yes. So if this one is going to be transparent because the process doesn't need to change at all. Whatever code you run will just change, will run as is. The OS is dealing with it for you. Okay, but you could say I change the application and I say you have some explicit code saying if connection break, re-establish, etc. That's also possible. Okay, but that's not going to be transparent. Okay. So this is a technique that you will have. So I just wanted to mention this because it is the hardest thing for most process migration systems to deal with. The other things are a little easier. Network connections are always thorny. Okay, so let me move on. If there are no more questions, I'll talk about two other things, which first of which is how can you do this if the system A and system B are not the same system, they're heterogeneous. Okay? And then I'm going to talk a little bit about virtual machines and migration in the context of virtual machine. But let's first talk about heterogeneous system. Okay? So all of what I said as far as moving memory and all of that was concerned implicitly assumed that machine A and machine B are the same architecture, run the same OS. Okay, everything is homogeneous. So you're moving from Intel machine to Intel machine. You're moving from Linux to Linux. You can't even move from Linux to Windows or anything like that in what we discussed. Okay? Now you could ask a question, what if the machine B is different from machine A? What if it's a different architecture? What if it's a different operating system? Can you still make migration work? Okay? The simple answer is it's not going to work out of the box. You can't just move memory, and if it's a different architecture, it's not even going to make any sense. The assembly instructions itself won't execute on the new processor. Okay? But what if the architecture was the same, the OS was different? Can I move from Intel to Intel but Windows to Linux, or Linux to Mac? Is that possible? So there are all. This is not an easy problem. It's complicated. Okay, so you could say I don't move processes. If it's heterogeneous, why don't you just move the code and then re-execute the code? So if it's a Python script, doesn't matter, right? If so long as your Python on your new machine, well, who cares whether it's the same OS or not? I mean, so long as you're the same version of Python, I just execute it there. Okay? Or if it's a Java program, so long as your JVM, the heterogeneity of the platform doesn't matter. Okay, you can run Java code across platforms. It is portable. So long as you have the same JVM on both of those machines, it's fine. So heterogeneity can be handled much more easily if you have code migration, weak mobility. Process migration is much harder. There have been some efforts that are trying to make it work, but it's not easy. Okay, so essentially what happens in this case, there's a complicated picture here which you can ignore, but essentially what needs to happen is the only way this process is going to move is this binary code is not going to work as is on a different architecture. You have to actually have access to the source code. You have to recompile it, okay, so that you construct a new binary that's going to work on the target. That binary will take the place of the code segment that was on the original. Okay? But then somehow the data has to be moved and it has to be interpreted accordingly on the new architecture. Okay? So what this is saying is you can transfer the data. The code cannot be transferred because the binaries may not actually work. The assembly instructions family itself may be different. So you have to recompile the code. And even after all of that, there may be things like pointers and whatnot in your code that might not work exactly the same. So it may be that you went from 32-bit to 64-bit architecture. Every int is now longer. So all of your data structures take more space. So if you have pointers and you made assumptions about how large your objects are, they may not hold on the target machine. So this is not a trivial problem at all. It's not even a solved problem, but there have been some efforts where people try to send under special assumptions. Okay, you can say, I make some restrictive assumptions, then I can make it work under some very specific scenarios, but it's not a general purpose solution. Okay, so if you have heterogeneous machines, code migration is possible, okay, because you're simply moving a code. So long as it's script, it's even easier. Python script and things like that is much easier. When you have binaries, things get harder. If your processes which are executing binaries, they get even harder. Okay, is that clear? Any questions on this before I move on? Yes? No? Okay, so let's leave that aside for a little bit, and I'm going to talk about a different kind of migration, which is virtual machine migration. Okay, and so in this case, we are not going to migrate a process. We are going to migrate the entire virtual machine, which includes the OS and all of the processes in it. Okay, so processes will move. They'll move as part of the virtual machine itself, moving from one machine to another. Okay. So I'm going to describe how it works. Then I'm going to tell a little bit about what kinds of advantages that has over some of what we talked about. Okay, so virtual machine migration involves moving processes. Okay, so let me show you with a picture what's going on. And just to understand why we are even talking about it, this is by far the most common way by which things are migrating. Okay, virtual machine migration is very common. Okay, in any data centers or any systems environment, it's very trivial to migrate a virtual machine. Every virtual machine platform supports this out of the box. Okay, so this is how actually a lot of process migration is occurring in today's systems. Okay, so that's why it's good to understand a little bit how this works. Okay, so let's take our hypervisor. Okay, and this is machine A. Okay, you have a VM. Here is your hypervisor. And this is machine B. And what we want to do is move this virtual machine from machine A to machine B. Okay? That essentially means that any OS that's running here, all the applications that are running here, everything just moves over. And the virtual machine starts executing on a new server. You're moving it from server A to server B. Okay? And the way this works is the following. Okay? You are essentially going to have to transfer all of the memory state over from machine A to machine B. There's one assumption that we will make, a simplifying assumption that we can then relax later, which is that the files this is accessing on a disk, okay, is on a network file system, which means that those files remain accessible here as well. Okay? So think of that, if you know what NFS is. Okay? Think of it as all the files that the virtual machine is accessing is on an NFS server. So when you move over, the data is still accessible over an NFS server. So I'm not going to worry about moving this data, although that can also be handled. Let's just ignore that for the moment. Okay? Let's just worry about how the machine actually moves. Okay? And now the interesting thing that we are going to do here is we are going to move the machine, virtual machine, while it is executing. Okay? You could have just said pause the virtual machine, just as when we said in process migration, I freeze the process. So its memory stops changing. It's not going to change. And then I copy the memory. Here we are going to say, let's not do that. Let the virtual machine execute. Okay? That means it's continuously executing, processes are running, they're changing the memory. While all of that is happening, I'm going to move this virtual machine from A to B. Okay? And here is how virtual machine migration is going to work. Okay, let's say this memory is just a collection of memory pages. Okay? In RAM, in hardware, you essentially have memory pages. Okay? So we are essentially going to, let's just number them 1 through n. Okay? Just for simplicity. Okay? So we'll say, just go in sequence and just start transferring pages. Right? So you transfer page 1, you transfer page 2, page 4, and so on. Okay? And you transfer n. Okay? So you are just marching through sequentially and moving all of the memory pages over. Okay? Once you're finished, one scan through the entire memory contents of the virtual machine, you have a copy of that virtual machine on the new server. Okay? But keep in mind that the virtual machine was continuing to execute while you are doing this. Okay? So you might have transferred some memory pages, but while after you transferred it, maybe the process ran and it wrote something to memory, or it did a new malloc or something, so the memory changed. Okay? So as a result, once you have finished the first round, whatever is here is not going to be the same as whatever is here. Okay? The origin has now changed because some data that you have sent over is now staying. Okay? It changed after you sent it. Okay? So the hypervisor can keep track of what changes are taking place because it knows what is going on. So what it will do is it will say, okay, I sent 100 pages. While I sent, what happened? It was maybe 10 pages changed because the process was executed. Okay? So in the second round, you're going to reiterate and say, send only those pages now that have changed since the previous iteration. Okay? So first you sent n. Next time you are going to send maybe n prime, and n prime might be smaller than n because not everything changed, only some subset of the memory changed. Okay, so you only send a subset that changed since the previous iteration. Okay? So in round 2 you might send some more pages. Okay, so some pages are unchanged, so now you will send some n prime. Okay, so now I updated some of the pages that changed. Okay? And you are going to recurse because once you in round 2 while you are sending the memory kept changing. So now in round 3 you say what has changed since the previous iteration. Okay? So you send some more pages over and so on. Okay? And the assumption here is that in each round you are sending less and less number of pages than the previous round. Okay? Because maybe first time you send 100 and when the process is executed, that you don't change everything in memory, they only change certain parts of memory. So you only have to send a subset of that 100 in the next round. And time it takes you to send that smaller amount of data is smaller than the first round. Okay? It takes you more time to copy 100 pages than 10 pages. So since there's less time, there's less execution, so there's even less changes occurring in that much time period. So in the next round, you will have less data and so on. Okay? So you will do this, or rather the hypervisor will do this in rounds for some number of rounds. Okay? Eventually you will hit a point where there's very little that has changed since the previous one. Maybe only 2 pages changed. Okay? So at this point you say, let's temporarily freeze the virtual machine. Okay? Send those 2 pages over, which is very quick. Okay? Because you have very small amount of data you need to send. Okay? So you're going to send that data over. And at this point in that last round, this virtual machine is frozen. It's not changing anymore. Okay? Because you paused it for a momentary period. You send the last amount of data. At this point, the memory contents on virtual machine A and virtual machine B are identical. They are synchronized because everything that's in memory of A is now in the memory of B. Okay? They're completely identical virtual machines at this point. Okay? So what you can do at that point is simply terminate this virtual machine and just resume execution here. Okay? Because they're exactly identical. If you start executing it, you will basically have the same thing happening here. Okay, so you can just essentially say this is gone, I terminate it, and then you resume. Okay, so this allows you to take an entire OS, all of the processes that are running on that OS, to move live. This is called live migration because the OS is continuing to run. There is no downtime. Okay? So you can have Windows or Linux or any of your OS running here, all the applications running, they simply magically appear on a new machine after some period of time. Okay, without any downtime, there's nothing. So the applications, processes don't see that anything has actually stopped at any point in time, except for that momentary freeze in the very last round where you send the last bits of data. Okay? But that freeze is so small that it is not noticeable. It could just be that looked like the hypervisor didn't schedule the VM for a small period of time. That's all it looks like. Okay, so this is called live virtual machine migration, which most VMs like VMware and all of them, KVMs, and they all support. Okay, yes, question.
Could I also do that from a VM to, say, a Linux VM to a Linux machine, or vice versa?
So in this case, so long as the hypervisors are the same, okay, the VM can just move exactly. So if this is a VMware virtual machine, it doesn't matter what the platform is, so long as this could be VMware running on Windows, doesn't matter, because what matters is the format of the virtual machine and the hypervisor. So the hypervisors have to be the same. Okay, the underlying platform, if it's type 2 hypervisor, this could be Linux, that could be Windows, doesn't matter, because you're just taking a VM and running it exactly the same way here.
And without using a VM on the receiving side, would that also work?
You mean to say this is not a VM?
Yeah. It's
No, I
just,
think this is just virtual machine migration. So you're just migrating a virtual machine, not just moving an OS and starting it on a different machine. Okay. Now there's only one last detail to discuss. And then I said that the disk you don't need to move because all the files remain accessible. Okay, but you could have done the same thing for disk as well. Could have moved the disk in rounds and slowly all the contents of the disk here appear there. Exactly what you did for memory. But let's not worry about that, but go to another question, which is what happens to network connections, which is a more important problem for us to talk about. This question.
I mean, virtual machines have virtual network cards, right? So I guess the thing that we could worry about for network connections is the same port on machine B available for use? If it is, then it'll be identical. If not, I guess
Okay.
would you have to wait for?
Yes, so I think you said something that is going to be relevant to how this is handled. We'll just erase all this. Okay. Okay. Now, it turns out that in this case, even though the VM has appeared on a different machine, handling network connections is actually very simple. Okay, not much has to be done. Everything just works as is, and all that you have to realize for why this works is the following. This is your machine A. It has an Ethernet card, okay, which has an IP address associated with it. Because this is a virtual machine, okay, it has its own logical Ethernet card. Okay. And the logical Ethernet card looks exactly the same as a physical Ethernet card, just an emulation. So technically, this has its own IP address, which is distinct from the IP address of the physical machine, okay, because every Ethernet card gets its own IP address. Okay. So even while this VM was running on the original machine, there was an IP address associated with the VM. There was an IP address associated with the physical machine. Okay. Clearly, this IP address is not going to move here. This machine is going to have its own physical Ethernet card, which has an IP address too. Okay. So that doesn't change, but that doesn't matter from our perspective. We are moving the VM. So essentially, this logical link and its IP address is portable. It's not attached to this machine. It's attached to the virtual machine. Okay. So when you move this virtual machine over, okay, its logical link and its IP address also move over. Okay, because it's almost like, think of it as if I unplugged the Ethernet card on one machine and I plugged it into another machine. You're logically doing the same thing by saying this Ethernet card is going to be a physical card, it doesn't move. This is a logical Ethernet card, that's just a piece of software. Okay? And this IP address associated with it, that is just attached to the VM, it has nothing to do with this machine. So you just move it over. Okay? So IP address moves over, and there's only one last detail you have to deal with, which is there's going to be network switches. Okay? And there's a network switch is connected here. Okay? And this switch was forwarding all the IP addresses, rather packets associated with this IP address to this physical machine. Okay, just saying that if there is a IP address for packet for this VM, send it to this NIC. Okay? Now, when you move this over, the switch might still continue to send some packets there, and that is simply addressed by doing what is called an R packet that just tells the switch clean out your state and relearn. Okay, because Ethernet switches are very flexible. You can unplug something from one port and plug it into another port and it still works. Okay, so that requires you to just say, forget that what you are forwarding here, go and figure it out again, saying when the packet arrives, which machine to send it to. Okay? So that's just a software packet that you send to a switch. Okay, that said, forget anything you learned. Okay, this is not routing or anything. This is just forwarding inside an Ethernet switch, which is all soft state. Yeah, because if you actually played with an Ethernet switch or your home router, you can plug in something from one port and plug it into another port. It just works. The switch just figures out that packets for that new device is now on a different port. It just looks the same way. It just assumes that this is now appeared on a different port and it just reforwards. So really in this case, connections don't break, IP addresses don't change, machine takes its IP address where there is a hopping around in the networks, appears on a different machine, the switches figure this out and not much changes at all. Okay? So this is a very powerful technique because it addresses a lot of what we are talking about. In process migration, moving network connections is actually the most complicated part. Okay, in virtual machine that becomes very straightforward simply because virtual machines have the luxury of having their own logical network interface, a logical Ethernet that they can take with them when they move. Okay, processes can't do that, okay, but virtual machine can. Okay, is that clear? Yes, question.
So when you perform VM migration, all the applications running on VM1 move to VM2?
Yes,
Or
so
can
everything is
choose
going to be
which
exactly the same. The OS is moving, OS is a process.
So everything above it moves.
Everything moves exactly. It looks exactly as if you could have just might as well started the VM on this machine. So everything, the OS is moving, the processes are moving. Okay, it's almost like this never existed. The whole thing is moving. It's not moving individual processes. Okay, I'm just simply moving the entire VM over. Yes.
Is there usually like a backup during the migration?
Is there a backup done?
Yeah, from the like the virtual machine one moving to the VM2. Is there like a backup for like VM1? Assuming like there's a crash in between.
Okay, you are asking a different question saying, can you actually do this and make VM1 a backup? So that's it. So this same technique that I talked about where you move the memory state is used in many other contexts. One of them is replication. Okay? So you can do continuous replication. So there's a backup copy of the VM. So this hardware crash that can take over. But let's not worry about all of that. That will come when we talk about fault tolerance. That's chapter 7. All we are talking about here is I want to move or migrate a virtual machine. How do you do that? Okay? Yes, after you move, there are 2 copies here. Okay, we are saying that we terminate this, so there's no backup kept right now when you talk about migration. But you could have kept it for other purposes. Okay.
So you said we have to clean the switches tables,
Yes.
but then it would only work within the same network, right?
Yes. So that's a good point. And the point is, if since we have to clean the switches, I should mention that this is typically done inside a LAN, okay, local area network. You can't just move it across the internet and expect it to work. Okay? If you wanted to do that, then networking becomes a bigger hassle because you have routers involved. Okay? Changing routing state is much harder than changing forwarding state in a switch. You can't, you can do it, but it's much more complicated. So it is transparent and easy only within a local area. That's an important point to keep in mind. Okay? So this is, you can think of it as live migration within a lab. Any questions on this? Okay, so that is essentially virtual machine migration. There are there's a couple of reading papers I'm going to put up because this is not in the textbook. Very nice papers. They explain exactly what I said. Go and look at it if you have any interest in knowing more about this. Okay, this is been used. Needless to say, this technique is actually used in data centers for doing load balancing and things like that. It's a very powerful technique. Right? So what you could do is, if you run a VM on some machine, let's say the virtual machine gets overloaded, okay, because lots of requests come out, there are 2 VMs and both of them start computing, you can just transparently move this VM onto a different machine. Maybe this machine has more cores, more RAM or something like that, and now it gets more resources. Okay? So it is actually used for load balancing across a cluster of servers where you can move these VMs around. The nice thing is there is no downtime at all. You can do this while your application, whether it's a web server database, just continues to run. Nothing else sees that this has even happened. Okay, so you just know internally you actually moved a VM. The mapping of the VM to physical machine has changed, but applications running inside or outside don't see that change. Okay, so it is used to do load balancing and other optimizations in data centers or large cluster of servers. Okay. All right. So one last case study before we move on, and that's another common case for code process migration. The most common thing where this is used is actually malware, where a malicious code is migrating from one machine to another, propagating itself, and then using it for bad purposes, malicious purposes. Okay? So this is exactly how viruses and malware spread. They are example of mobile code, not processes. That's code migration, not process migration, except that you are using backdoors or bugs within the machine to inject code into a new machine and execute it. And then it will basically either steal data or it will try to self-propagate to other machines and so on. Okay? So viruses, malware are an example of mobile code, and they use code migration to jump from one machine to another. Okay? This is by far the longest serving use case for process and code migration. It's not the most useful one, but that is essentially how some of this code spreads from, or malware code spreads from one machine to another. Okay? And again, there is sender initiated, receiver initiated. If you basically have viruses that spread themselves, that's sender initiated. Virus on machine A is looking for vulnerable machines on the network and then spreading itself. Okay? Receiver initiated is you basically get a phishing message saying your bank wants you to provide some information. You click on it, it just goes to a phishing website, not a real website, and now that might download some bad code or steal some information. All sorts of bad things can happen. Okay, so that's receiver initiated version of a malware. The same kinds of things are true even in this scenario. Okay, so I will, in the next 10 minutes, introduce the next topic, because we still have 10 minutes to go. We are going to go to the next chapter in the book. So we just finished over the past 3 or 4 lectures, processes, threads, virtualization, migration. So it's been a set of things we have covered so far. Okay? That's all deals with the CPU aspect of distributed systems. Okay? What happens as far as the processor is concerned. Now we are going to look at the networking aspect, which is equally important, essentially communication in distributed systems. Okay? So in the next 10 or so minutes, I'm not going to give you a very high level introduction, but next time we'll talk about remote procedure calls or RPCs. Then we are going to talk about remote methods, okay, RMIs, that's what is used in the Java world. Okay, and then I'm going to talk about stream-oriented communication, which is audio, video streaming. Okay, these are all examples of communication. In one case, you send a request, receive a reply. In another case, you send a video file over a network, and then some the other end might play it out and so on. So we'll talk about all of these things in the next 2 or 3 classes. Okay, so let me start with just a quick introduction for communication. Okay, so communication is inherent in distributed systems. Okay, if you think about the definition, we said it's a collection of processes or processors that communicate over a communication medium, typically a network. Okay, so in the distributed system, your entities that communicate. And then there are 2 ways by which they can communicate. One is unstructured communication, the other is structured communication. Okay. In unstructured communication, you communicate through memory or shared memory. Okay. Essentially, you put some data in some piece of memory. Okay. Some other process goes and takes that data and processes it. Okay. That is called implicit communication. Okay. So you're not sending any explicit messages, but there is just some piece of shared memory. Okay. This is memory. Okay. It might even have data structures. So machine A or process A is going to write to it or modify it, and then when D reads it, you have implicitly communicated something from A through B through a shared data structure. Okay? So this is essentially called unstructured communication or implicit communication. Okay? Most communication will not be implicit, it will be explicit, which involves message passing. Okay? Essentially that means that process A is going to send an explicit message over a network to process B, and then you might get a reply, which is another message. Okay, so this involves sending and receiving messages. Okay, so that is referred to as structured communication, which is explicit message passing, also called IPC, inter-process communication. Okay, so distributed systems will use both, but we are mostly going to focus on this in this chapter. Okay, when we talk about some other things, we might come to structured communication, but right now we are going to look at structured communication. Okay, so very quick recap of networking, which you may know, so bear with me, but just in case you don't, I'm going to tell you a little bit about what's a protocol, how it works, and so on. Okay? So you need to know some networking in order to understand how message passing and things like that work. Okay? So what is a protocol? Protocol is essentially a set of rules for communication. Okay? So in this case, all parties that are involved in communicating agree on a set of rules. Okay? And then you communicate based on those rules. And these rules are called protocols, and there are different kinds of protocols. So here is what is referred to, this picture is showing you what is referred to as an ISO network stack. Okay? What this means is the networking subsystem has a number of layers associated with it. Okay? So this is the layered approach, and each layer implements a protocol that performs a certain task. Okay? At the very top, you have application on machine A and application on machine B. Yeah, they use application level protocols. This could be HTTP. Okay? That's an application level protocol. Okay? A web server and a web browser communicate using the HTTP protocol. Okay? If you have email, that's SMTP protocol, simple mail transfer protocol. In this case, the mail client and the mail server are the two applications. They are using SMTP, which describes how a message has to be constructed, what are the headers, what format it has, and you send it off. So those are application level protocols. Now, there are many others. So let's start on the bottom. The physical medium is basically what you have, which could be, if it's a wireless communication, your medium is the air, or that sort of channels on the air. If it is wired communication, your physical medium is an Ethernet wire. Okay, so this essentially is the physical layer of your network subsystem. Okay. The next layer above it is what is called the data link layer or the MAC layer. Okay, so in this case, this says how do I communicate using Wi-Fi, how do I communicate using cellular, or how do I communicate over the Ethernet, what is the structure of packets that I send, they are called frames in Ethernet technology, frames that I send from machine A to machine B using Wi-Fi or cellular or things like that. Okay, so that's your MAC layer or data link layer. Then the layer above it is called the network layer. Okay. In TCP/IP world, this is where IP resides. Okay, this internet protocol. IP layer is responsible for hop by hop communication. Okay, one hop to the next, one machine to the next. Okay. Typically, communication is not going to be direct. It might involve intermediaries, which are typically routers. Okay, so your packet goes from the machine, it goes to a router, it goes to multiple routers until it reaches the destination. Okay, from one machine to next along this path is what IP is going to be responsible for. At each node in the path, IP is going to look up its routing table and say, where does this packet go next, so that it eventually gets to the destination. Okay? So that's purely hop by hop communication. Okay, so basically, if your packet requires multiple hops or steps to get there, IP or the network layer in the TCP/IP world, that's IP is operating at the network layer, is going to do routing. It's going to route packets from the sender to the destination. Okay. No question there? So the next layer up is the transport layer. Okay, so this is where TCP would sit in the TCP/IP world. Okay. And TCP is responsible for end-to-end communication. Okay. The IP or the network layer does hop by hop. TCP does end-to-end communication, or responsible for it's a protocol that does end-to-end. So it looks like things like what speed should I send packets? Okay, that's the rate at which you send packets. Okay? If packets that are sent are not received or are corrupted, it deals with how it should, when to resend them so that they're eventually received. So it does error checks, it tries to figure out when packets are lost, it does retransmissions. So all of this is handled by TCP, okay, or the transport layer in this case. So it basically says I sent a packet, or I'm sending packets, how fast should I send it? And if you don't receive it, when should I resend it? How do I figure that out? You did receive it, or should I retransmit it, and so on. Okay? So that's TCP. And then you have the session layer protocols. If you have used sessions between the two endpoints, those are handled at the session layer. Right? In the TCP/IP world, there is no session layer or there is no presentation layer that's mentioned there. Those are all sort of the responsibility of the application. If you set up an HTTP connection and create a session, typically in the web it's dealt by application. But in the ISO stack, there is actually a session layer protocol, presentation layer protocol. These might do things like encryption. And you might say, every packet I send is encrypted. So if you use SSL or HTTPS, that would technically sit at that layer. Although in the TCP/IP world, that's all part of the application. Okay? So this is a very quick overview of a typical protocol stack. You may already know this, but if you haven't taken a course in networking, this gives you like a 5-minute refresher, not a refresher, but a summary of what communication protocols are. Okay? And before I go into why I'm talking about this, let me just tell you a little bit about the structure of a network packet. Okay? This is what a typical network packet looks like. What is here is the actual message that is being sent by the application. This is also called the payload. Okay? Now, typically, as the packet traverses through the protocol stack, each protocol layer is going to attach a header to it. Okay? So this is like this was a web browser that was sending a request, a URL. This would be the HTTP header that gets tagged on to the message. Okay? And then the application layer protocol, I should have mentioned one more thing, which is when an application communicates, the packet originates at the application, it traverses down the protocol stack, and the OS is going to send it out on the network. It's going to traverse through the network, appear at the destination, and it traverses up the protocol stack and is handed over to the receiving application. Okay, so it goes down the protocol stack at the sender, it gets received and processed upwards at the receiver. Okay. So what that means is when it's traversing down, you start with a message. Each layer is going to add its own header that indicates to the other end what is going on. Okay. So this could be the HTTP layer. Okay. Then this could be the TCP layer or headers. Okay. The TCP headers go here. The IP headers go here. The Ethernet frame headers go here, and so on. Okay. So as the packet actually goes over the network, this message that you started with has a number of headers associated with it that have been tagged on it. Okay? And when it appears at the other end, okay, each layer is going to actually look at the header, okay, decide what to do with the packet, strip that header and hand it to the layer above it. So now layers or these headers are getting stripped out, and eventually this message will get delivered to the application as it originated from the sender. Okay? That's typical protocol processing. Okay? Packets are going to have headers. You go down the protocol stack, they appear at the other end. Okay. Now, in the TCP/IP world, because some of the layers in the middle don't exist, we are in our case we are going to add middleware protocols there between transport layer and the application layer. So when we talk about middleware, some of those protocols are actually sit between TCP/IP and the application. Okay, so we are going to look at a number of different middleware layer protocols. Yes, we look at synchronization, locking, leader election, a whole bunch of them in a little while. But keep that in mind. This is where they sit. This is where the middleware would also sit in our protocol stack picture. Okay? Any questions here? Okay. So I'm going to just show you one slide, but I will talk about it next time because we kind of run out of time. And this is a slide that shows the message exchange for TCP. Okay, I don't know how many of you know how TCP works, but whenever a TCP connection is established between machine A and a machine B, it involves exchanging 3 packets to establish the connection. Okay, these are called the SYN packets. So you'll see that if the client wants to set up a TCP connection to the server, it sends what is called a SYN packet, okay, which is essentially going to tell the server that I want to set up a new TCP connection with you. Okay, and then the server is going to send an acknowledgement packet saying, yes, I received your packet, and it's going to send a SYN in the other direction. Okay? And that says because the connection is duplex, is bidirectional, you need to set up 2 unidirectional connections in order for the communication to take place. So the reverse SYN is tells the client saying the server wants to set up a connection with it in the reverse direction so that packets can go in both directions. Okay? Okay, so that SYN comes and there's an ACK to the original SYN that comes. And then the client is going to send an acknowledgement to the SYN saying, yes, I received your SYN packet. Okay? So these three packets have to be exchanged. This is called a three-way handshake in the TCP world. Okay? These three packets have to be exchanged before any real communication can start. At this point, nothing actually has happened from an application standpoint, just that the TCP at both ends have established a connection. Okay? Only after this can you actually send a real request. Okay? So if you are trying to send an HTTP request, a browser wants to make an HTTP request to the server, first it has to set up a TCP connection that will involve three packets. Okay? Only after this can it send a request. Okay? And then there may be arbitrary numbers of requests and replies. And then once you're done with the connection, you have to send what is called a fin request, which says I'm finished. Okay? SYN stands for synchronized, fin stands for finished, saying I'm done. Okay? And then you will get back an acknowledgement and you'll get a fin in the other direction. Okay? So essentially there are three packets that are exchanged at the beginning, three packets that are exchanged at the end, and then arbitrary number of packets in the middle that involve actual communication. Okay? That's how TCP works. Okay? Next time I'm going to show you why that is not necessarily the most ideal case for simple request response client server applications, and we are going to see what's shown in the next picture, and optimization for it. Okay? But today let's stop here.